So this is a slightly trickier sheet. I guess somehow the maths is trickier because these are quite tricky little puzzles to solve if you haven't seen them before. So what's going on here is we were talking about groups, and we had 5 axioms defining a group before, but as the great John Thompson taught me when I was a first-year undergraduate, you can get away with 3. If you just have these 3 axioms, associativity, and then one of the multiplication, 1 times A is A, and A inverse times A is 1. If you just have one of the identity axioms and one of the inverse axioms, you can prove the other 2 from those axioms. And a kind of a nice way of doing that sort of thing is doing it in lean, because it can get quite muddly if you're doing this on paper. You accidentally sort of forget which axiom you have, or which one you're trying to prove, or whatever. So this is a nice little exercise to do in lean. So how are we going to prove that if we have a weak group, which is something with a 1, a multiplication, and an inverse that satisfies only these 3 axioms, how are we going to prove that it satisfies the other 2, mul1 and mulinv self? So presented without any clues at all, that's really quite a tricky problem, but I've given you these hints here. So first of all, we should prove mulinv cancel, which I claim is this result here. There. So let's try and prove mulinv cancel. So I guess we should start with intro. It's a bit silly. Proofs that start with intro, you can often just fix them by changing the statement of the lemma. Let's make H a hypothesis instead of just having to ask there. So if we rewrite the lemma slightly, lean still thinks this is the same lemma, but you see if I do check at mul left cancel there, it still says A times B equals A times C implies B equals C. It's just that we don't have to start the proof with intro H. So how are we going to prove this lemma? Well, the maths proof is that the idea is we know that A times B is A times C. So A inverse, this is the point. The trick is that A inverse times A times B equals. There's 2 ways of evaluating A inverse times A times B. We can either use H to get it to A inverse times A times C, or we could use associativity to put the brackets around the A inverse times A. And the point is that A inverse times A is 1, and 1 times the 2 axioms we have are exactly the 2 axioms which will enable us to cancel this. So we could do how could we do this? We could do have H. We could do A inverse times A times B equals B, and that shouldn't be too difficult to prove. So that would be associativity. So associativity is in the right place here. So we could do. I was going to say we could use the simplifier, but we can't use the simplifier. So because these are weak groups, not groups. So we need to rewrite this. And now 1 times B is B, so we rewrite 1 mul as well. So that's the proof of that. Now we've got 2 hypotheses called H. That's not very clever. Let's call it H2. And now we could rewrite H2. And now the idea is to use associativity there, because now we've got an A times B, and then we can rewrite H. So maybe we can do all this in one go. Mulassoc. Let's close this bracket to see. And now A times B is A times C, so we can rewrite H. And this is now A inverse, so now Mulassoc again the other way. And now we've got an A inverse times A, so that's inv mul self there. And now we've got a mul1. No, we've got a 1 mul, which is good because mul1 is what we don't have. So there's a proof of that. So there is actually a way. Let me show you a different way of doing this. You look at this proof and it's difficult to follow, right? So let me show you actually a completely different way of presenting the same proof, which is rather easier to follow. So we can use the calc mode. We can use the calc tactic. And the calc tactic looks like this. Let me just set it up. B equals whatever, sorry, ... equals C, sorry, there. I always like to start off by setting up the calc tactic. Maybe it can go down. We can go down like this. There we go. There. Let's put some spaces here. Okay. So the idea is that we're gonna do lots of lines like this. We're gonna argue. We're going to argue B equals 1 times B. That's the first line there, and the proof of that is by rewrite 1 mul, I guess. 1 mul is the one we have, right? Yeah. So B is 1 times B, and that equals A inverse times A times B. There. Can I get these? Shall I line these up with this? I'm trying to make it look good. There, and that equals A inverse times A times B, and that's by rewrite. That would be inv mul self, I guess. There, and that equals A inverse times A times B with the brackets in the other way. So that equals this. There. Oh, I'm going to move those over there now. So that's by rewrite Mullersock. There. The nice thing about this is you never have to worry about rewriting left or right, because the goal, if you look at what the goal is to prove that this equals this. So you rewrite Mullersock, and Mullersock will whichever one it is, it'll rewrite it to the other one, and then it'll close the goal because of REFL. And now this equals A inverse times A times C. There. And that's our hypothesis, right? By rewrite H, and that equals, and now we put everything back, A inverse times A times C, and again that's by rewrite Mullersock. Again, you see that's the other way around. You see there, it's complaining that equals C. Sorry, there. Let's stop it complaining. I don't like having errors. The point here is that Mullersock now changes the right hand side to the left hand side, and then closes the goal with REFL. And this equals 1 times C, and that's by rewrite inv mul self, and that equals C by rewrite 1 mul. So that's a longer proof, but as you can see, it really has the advantage. This proof is now sort of really readable. So sometimes when I write lean proofs, I'm sort of guilty of trying to make them as short as possible, and somehow the shorter they get, the less comprehensible they become. But here, this is kind of a really sort of a comprehensible looking proof. What have I done? There. So there we go. There's mul left cancel, and now the second hint I give you is to prove mullic of ekim mul. So lemma this, and it's supposed to say this. So we've got our hypothesis that B equals A inverse times C, and we want to deduce A times B is C. And of course the point is we're going to use mul left cancel. So we could apply mul left cancel, and let's just see what we've got. And then you see lean can't work out. There's an A here, which lean doesn't know about. So if I got is A, oh great, A is explicit. If I hover over mul left cancel, you can see that AB is here in round brackets. So the next input that mul left cancel wants is the variable A. So in fact we can tell it what right now it says something times A times B is something times C. That's what we have to prove. But I don't know what that something's supposed to be. But that something is clearly going to be A inverse, right? If we let that something be A inverse, then our hypothesis H tells us that the right hand side is B. And the left-hand side we're going to be able to simplify to b. So we can put A inverse here, there. And now we can probably do everything with rewrites now. So now rewrite Mullersock that way. And then invmul cancel, sorry, invmul self. And then 1 mul. And then, and then H. And we're done. So there we go. And we could, if I was really developing the theory of weak groups, I could train the simplifier on certain things, but there's not really much point doing it now, because now we're nearly there. So both of the missing axioms now come straight from Mulleck of Ekim Mull, if I recall correctly. So let's try applying this, and now I've got to prove that 1 is A inverse times A, and I'm hoping that's the one we have, right? It is. It's invmul self. Invmul self. What have I done? Invmul self, and there we go. And similarly, this one as well. I'm going to apply. I'm going to do the same. I'm going to do the same thing here, and now I've got to prove that A inverse is A inverse times 1, and so this is going to be rewrite. You see, mul 1 we've just proved. There, great. So that's the end of those, and then you see, and then if we were doing this in Lean's maths library and sort of joining all the dots together, we would now define the function that, given a weak group, constructs a group, and there's the boilerplate that does all that. So finally, this is sort of very open-ended, and I didn't tell you anything about the sort of stuff you would need to do this. So the point about my even weaker group is that these axioms, I mean, it looks almost exactly the same, right? But the difference is I've got 1 mul here, and I've got mul 1 here. And if you switch that around, you see invmul self is the same, but 1 mul is not. So these 3 axioms here are not enough to prove that G is a group. And I can just give you an explicit example. So let me, to give you an explicit example, I need a set, right? I need a set with 2 elements. I guess I could just make one. Shall I make one? Let's, I mean, there's already a set with 2 elements called bool. Let me show you bool. Let's right click on this and go to definition. Bool is an inductive type with 2 terms, false and true. That's defined in core Lean. We're going to be careful not to mess anything around. If we mess up this, if I type a letter here, it will somehow really mess up lots of things. So bool is a type with 2 terms, false, FF and TT, called false and true. So what I'm going to do here is I'm going to make bool an instance of my even weaker group. And so let's do instance my even weaker group bool. I'm going to give bool this, this is like a set with, it's just a convenient set with 2 elements. That's what's going on here. I'm going to take a set with 2 elements, and I'm going to give it it's going to satisfy all the axioms of my weaker group. There we go. I just did a kind of a cool mathlib trick. So we have to say what. So let me just show you. We've got the 2 elements are called TT and FF. So check TT. You see that TT has got type bool, and check FF. FF has got type bool as well. So 1 can be TT. Why not? Multiplication is the function that sends lambda xy to something. I have to give it a bool, and the trick here, you define multiplication to be x times y is always x. So that's the insight there. This says x times y is x for all x and y. And then the inverse function is the function that sends x to 1, which is tt. And this you define x inverse to be 1 for all x. There. And now I claim that all the axioms work out, and we could talk about it if you like. X times y is x, so a times b times c is a times c, which is a, and a times b times c is also a. So that's going to be true. And mul 1, a times 1 is a. That's true because a times b is always a. You see, and invmul self is true because I've defined a inverse to be 1. And so a inverse times a is 1 times a, which is 1. So you can see all the axioms are true. and I mean, I could sort of carefully try and prove them, but because bool only has two elements, I can just say sort of check everything, right? Sort of deck trivial. These assertions are decidable because an algorithm for deciding them is just check all the possibilities. So deck trivial should, if I've got it right, should solve all of these. There we go. So there's the deck trivial tactic. And I guess it's not even a tactic there. I'm using it anyway. This is just a trick to say check all the cases. And now my claim is that so my bool is an even weaker group, but my claim is that bool is not a group. And to prove that bool is not a group, I'm going to show that one mul fails. So it's not true that for all G in bool, I'm going to prove mul 1 is true. I'm going to prove that one mul is not. 1 times G equals G. There. This is my claim. Begin, end. And so why is this true? So intro, we've got the hypothesis that for all G in bool, 1 times G is G, and we have to prove something. We're proving it by contradiction. And 1 times G, I know 1 times G will be equal to 1, and 1 is TT, true. So let's specialise H to false there. And now I've got this hypothesis that 1 times F is F, and I claim that that's not true. So let's try cases H. Will that do it? There we go. So there's a proof. There's a proof that my even weaker group is not strong enough to be a group, because I've given bool a structure of my even weaker group, and I've proved that bool does not satisfy one of the axioms for a group. So there you go. I mean, I wouldn't take this stuff sort of too seriously. I'm just showing you other things that Lean can do, some of which I haven't talked about in the course notes. So don't worry too much if you didn't follow that last bit.